What are you doing? Again. All right, so we'll give it a couple more minutes. Okay, so that's a couple minutes. So the first question that I was going to ask was I wanted to ask everybody how the mock qual went. I assume that some people had some time to look at it over the weekend, but there's 5 people here. So I guess that this will be a rather short asking you all how mock qual 0 went. And was it like easier than you thought, harder than you thought? Was it like it would have been fine, except that there's this problem in part C that was on a topic that Wilhelm never talked about this quarter? You know, like,
I think it was fair in terms of difficulty. That doesn't mean that I did well on it. There's definitely a few problems where I don't remember what locally finite means, for instance. So that kind of narrows down which questions I would choose to do if this were a real qual. So,
yeah.
But otherwise, I think it was decent.
I also skipped that problem when I took this qual. So
I ended up for that problem I ended up like just working through that one until like trying different definitions of what locally finite might mean, until I found one that worked. So I'm pretty sure I did it right. But like literally, like I was like, yeah. So this first definition does not work. It's just definitely false. This is not correct if I use this definition. And I like got through like 2 more before I found a definition that was like, oh yeah, this is definitely the definition that you want, because then these things are true. But like, I thought it was pretty simple. The only one that like, I mean, there were problems that I straight up skipped because I was like, no, I'm not doing this. I don't know.
Sure.
I don't remember I don't remember most of the stuff about like local homology groups and stuff like that, but like um uh the big ones for me were problems 4 and 5, because like I know how to do them, but like for 4, for example, like I'm pretty sure like right, what you do is you show that right, like roughly speaking, you say, oh well, X is basically a point. So every map from X to S1 is like mapping a point somewhere. But I don't know how to formalize. I don't remember how to formalize that. I'm assuming you pass to homotopy groups and you get something. And then 5, the thing that I need to like clarify is the phrases retracts and deformation retracts, I can never keep them straight. Like what order the maps are and which ones you refer to as the retract versus the section and everything.
Luckily, we don't need to know those definitions to do number 5.
Don't you? Because you need to know to show that Y is not a deformation retract, you need to be able to write down the order of the maps correctly so that
Nope. So for number 5, all you need to know is that if one space is a deformation retract of the other, they have the same fundamental group.
right.
And then you just say
okay, so,
this
so
subgraph does
I was
not
trying to
have
prove
the same
that
fundamental
by-
group as the original graph, and then you're done.
I was trying to prove that by saying, oh well, if one is a deformation retract of the other, then you write these maps down, pass to the fundamental groups, and you observe that the maps are actually isomorphisms. And I was trying to like get it from first. But if you're saying I can just remember that that is a fact that we have, then yeah, you don't need to know the order. But like if I forget that fact, I can prove it from the start, right? Because it's not hard to show that deformation retracts have the same homotopy group or first fundamental group. But like I ended up looking up definitions because I was like, I cannot remember the order that things go in. Also, especially since Hatcher uses slightly different terminology than everyone else on that.
Okay. Yeah. Yeah. I can't remember if Hatcher uses deformation retract as strong deformation retract, or if, because, okay, so there are like 2 schools of thought. Some people just call a retract as a shorthand for a deformation retract, and then strong deformation retract is its own thing. And some people are like, not like what other people call strong deformation retract, we call it deformation retract. What other people call deformation retract, we just call it retract, which is confusing. But both of these are fun. Okay, cool. Yeah, I actually skipped question 5 when I did this qual, and I shouldn't have, because question 5 was definitely the easiest question for part 2. I was like, I don't want to figure out the homology thing, so I just went to 6 because I had done that problem a couple minutes before, and I just threw it in this question. All right. Anyone else? How did Mock Qual 0 go?
Pretty good. I have been spending time on part C, and I definitely noticed that. Like, I had ideas on how to start all the problems, but by then my time was low. And like I didn't have time to figure out how to finish them. Like, even though they were like mostly questions we'd seen from class, like, so I had an idea of how to start, but not enough time to finish them properly.
Okay.
And then, yeah, I just didn't do question 6 from part B, and I wasn't sure if I could have done it. So that's something else to think of.
Okay.
Yeah, I don't know. I just chose basically the ones that exactly the same with the homework, and then I had an idea during the reviews, and I didn't try to look that much about the other question yet.
Oh, that's the good thing about this qual, right? You only have to do 2 problems from every group of 3. Right? So it's okay to not know problems as long as the problems that you don't know match up with 1/3 of the problems on the exam in a very specific way.
Yeah, I feel like for me, part 3 was the easiest just because I think all those questions I've seen before. I, I think Fred might have used the same exact questions.
He definitely did.
Yeah, like 7 and 9 were the ones that I chose from part 3. And 7 was you just have to remember one picture that he drew. And like
Right.
9 is a one-liner.
So that's one of the reasons. So I know people who wrote 1 line for question 9, and they did not. Fred was not very happy with that. Fred was just
Why?
like,
When I gave him that that solution for the class, he was like, "Yeah, it's one line."
okay. Okay, so I wrote an entire page for my question 9 when I did this qual, but that's because the mentality that I had for the qual was the point of this qual is to show Fred that I've learned something. Right. So even though it's 1 line, like this is a diffeomorphism between this set and this set, right? I also showed that an open submanifold of parallelizable space is also parallelizable space. And I just wrote like a short proof of that. And because otherwise I was like, am I seriously going to turn in a qual that only has 1 line for a problem? Because, yes, this, right? Like once you know how the solution works, it is very simple, but I also wanted to prove to Fred that I learned something, right? Because that's the goal of the qual. The goal of the qual is to not get all of the answers in the best way possible. The goal of the qual is to prove to the qualifying exam committee that you know what you're talking about, right? So, I don't know. The qual is weird, and that is, yeah, maybe because I never talked to him about it, maybe I could have written 1 line, and you're right, and I could have done that, but I'm a scaredy cat, and I wouldn't. Okay, so the point of today is to talk about some stuff from part B. That's what we're going to do this week, allegedly. And the way that I view part B is that there are 2 ways that you can group the topics in part B into 2 sections. The first section is homology, and the second section is everything else. My exercises to know list has mostly everything else. It has a couple homology, but that's because when I was typing up problems, I couldn't find good homology problems. So the worksheet that I make for Thursday will probably be focused on homology type problems, right? We'll calculate some homology and we'll look at some of the theorems for homology, right? So today we'll probably talk about everything else. Unless somebody really wants to watch me struggle through homology, then we can try to do something. Or we can also talk about problems from Mock Qual 0. That's fine too. And if we talk about
just unrelated, I'm looking back on it. He said, yes, it's for homework. He said it's fine to just do a 1-liner, but he'd want more details on the exam.
okay,
But
good.
then in the follow-up quote statement to that, he didn't clarify if I'd have to prove that open subsets of parallelizable manifolds are parallelizable, or whether I can just state that.
Yeah, so the way that I looked at that was that for this problem, there's 2 main things that you can prove, right? You can either prove that the function that you defined is actually diffeomorphism and go through the process of showing.
Oh no,
that,
that's not even that. I didn't even. He wasn't picking that at all. I just said. So the first part of what I said was the s to the n times r is diffeomorphic to the punctured space by give the map. That's obvious. He didn't have a comment on that at all.
Right.
Then since the punctured space is clearly parallelizable, we're done. And he just said, clearly parallelizable is maybe not the best. Like it's fine on homework, but for the exam, do more. And then I asked him, how would I elaborate on that? He said, R to the n, it's parallelizable. Open subsets of parallelizable manifolds are parallelizable. So it's not clear to me whether I have to prove that those statements, or whether, because I've said literally almost nothing. I just said, yeah, it's clearly parallelizable. To just add those 2 lines to justify why it's clear might be enough, but I'm not sure.
Yeah. So like I was saying, there are like 3 statements that like have meat in them, in my opinion, right? But actually 2, right? It's that is a diffeomorphism, and that open subsets of parallelizable spaces are parallelizable. And so what I did was I said, I'm going to prove one of them, right? And I chose to prove that open subsets of parallelizable manifolds are parallelizable. And then I also just said, yeah, Rn is parallelizable because it's clearly parallelizable, right? Like that part I don't think deserved justification, but like I looked through the argument and I said one of these, right, speaks to the heart of what this problem is supposed to be about, in my opinion, right? I've identified like the perfect model space, and then I just want to show that that model space is parallelizable, right? But I think that you could have probably gotten most credit by just choosing another one of those, the other statement that maybe, right, has meat, and it doesn't actually have that much meat. That's what I thought when I took this exam, but then I went back and proved that statement. I was like, oh, that's not very hard to show that this function is a diffeomorphism, right? So maybe I should show that open subsets of parallelizable manifolds are parallelizable. Right, so like I went through and I was like, what's the thing that Fred's gonna think is the hard part, and then I'm gonna try to do that. Yeah, and that's how Fred talks about the qual too. He's just like, I just want to see that you've learned something. Anyway, thank you for clarifying. Just to, okay, before we dive in, since we've spent a lot of time talking about part 9, maybe I should at least say, like I've been saying things like clearly this is parallelizable, or sorry, clearly this is diffeomorphic to, right, a nice space. Should I explain what that diffeomorphism is, just in case people haven't seen that yet, or have you all seen this? I mean, I know that Raul's seen it because he's the one that also said that this is.
I have also.
Okay. So I guess that then I will just write that for Mock Qual 0, number 9, that the diffeomorphism that I'm talking about is the it's the like higher dimension polar coordinates map, right? So in regular polar coordinates, right, you have your plane and you remove the origin, and then you say every other point is determined by a distance and an angle, but instead you could determine that angle by just saying that it's a, how come Control Z isn't getting rid of my prior marks? That's annoying. I can't just delete things, right? Instead, you could just take a point on the unit circle and scale it by r. And that's the same as choosing an angle, right? So this is just the higher dimensional analog of that, right? You, right, first you map r to 0 infinity via the exponential map, which is a diffeomorphism, right? And then you do Sn cross r goes to Sn cross 0 infinity via this map up here. And then via this polar coordinate map, you go to r n plus 1 minus the origin. And so this is just the identity in one coordinate and e to the x of the other coordinate, which are both diffeomorphisms. So that's a diffeomorphism. And then the product of two smooth maps is smooth. And then you show that this is a bijection. You get that this is a diffeomorphism. So this is just one of the things that Fred likes to do is he likes to give you questions that look hard but are actually just subsets of Rn. Right. So learning some of the ways to identify things as Rn is useful. Right? You know, so same thing with like removing a point from Sn, right? You should be able to, you know that that is diffeomorphic to also Rn, right? Sn minus a point is diffeomorphic to Rn. So, right. Because these are the kinds of things a friend likes to do, right? He likes to be like, oh, this looks so hard. And then you apply diffeomorphism. You're like, yay, it's Euclidean space. But that's part C stuff. We're supposed to be talking about part B stuff, I guess. Allegedly. All right, do we have any questions or something from part B that people would like to talk about? Hey, Shannon.
Yeah.
Good morning. Thanks for the shout out in the other video. I'm like, that was me. What are we doing today? Sorry, I have a thing until like 8:35, so I'm always late.
Part B. So algebraic topology stuff.
Same work, okay. Different worksheet.
Not a worksheet today, but you know, we have like the exercises to know and the mock qual questions and stuff. Yeah, and I just said that I tend to lump, there are two groups of topics in part B. There's homology in the first lump and everything else in the second. So we're probably going to do everything else today, and then we'll do a worksheet on homology on Thursday. All right, so I think Ryan was speaking before I rudely interrupted him.
Yeah. Could you look at question 4 on the exercises to know in
Exercises.
yeah. It's about the connected graphs and the valence vertices.
Oh yeah. I love this problem. I was really hoping that someone would ask me about the question.
What is a
Because-
valence vertex? Did Schultz mention that ever?
He might have called it the degree of the vertex. It's just the number of edges connected to that vertex, where you count like an edge, which is just a vertex connected to the same vertex.
Right.
as two.
Okay. Yeah. Okay. Degree makes it sounds something that I've heard.
So the reason that I really like number 4 is because you can solve it using induction.
Mm.
Which I think is just awesome. Unfortunately, okay, so the first thing is that there's a typo on this problem. You need to have a finite number of vertices. This fails if you have an infinite number of vertices. How does it fail? So here's the counterexample for infinite graphs. On one side, I'm going to let G1 be the regular 3-valent tree. And so you've all seen this. It's like the infinite binary tree, right? And this is like part of something else, and that goes like this, and this goes like this. Right? And on all these branch out into whatever. Okay. That's most of the graph, so I'll stop drawing it. And in G2, we are going to take something which is not a tree, so they won't be homeomorphic.
Triangulate the plane.
Yeah, you could try. If you triangulate the plane.
Oh, sorry, no, that would give you more than 3.
Yeah.
Sorry,
Yeah.
I mean,
So
yeah, you can modify the first one.
yeah. So the one that I was thinking of is you actually take this graph, which you've all seen. And right now this is not a counterexample because these edges have, and what you're going to do is you're going to replace intersections with these little diamonds. So at every intersection on this, right, you're going to replace this intersection with this little diamond, right? So now every vertex has valence 3, but the graph on the right is littered with loops and it's not a tree, but the graph on the left is a tree. So the graph on the right has non-trivial fundamental group and the graph on the left has trivial fundamental group. And so therefore these can't be homeomorphic because they're not even homotopic. Write down what question you're doing. So this is exercises to know part B, question 4.
This is cool. Do you know what the fundamental group is for the graph on the right
Oh,
with the diamonds?
I think it's F infinity. If I had to guess, because there are no relationships between any of these.
Right.
Yeah, because this is actually one of the theorems that you talked about in part B, that you calculate the fundamental group of a graph just by calculating its Euler characteristic. And this has infinite Euler characteristic because it just has like an infinite number of attributes. And fundamental groups of graphs are always free, which is nice. So once you know that there are an infinite number of generators, there's only one choice.
Yeah, I'd like to see 10, 11, 12, like any of the big kind of like either showing like what like universality properties, you know, showing the commutativity of those diagrams and then getting the fundamental groups of those last ones with the little threads. I didn't see anything like cohomology on there, but so any of those would be kind of fun.
Yeah, so the part B sequence here does not cover cohomology. So you do not need to know any cohomology for this qual. But if you take the algebraic topology elective, that's where you get some cohomology. So, which is great because you don't have to know cohomology.
Right, in a testable manner, right? Yeah, but otherwise, 14 looks cool too with the homology part, but that's my 10 to 14.
Okay, so sure, let's finish 4. Right, so this is a counterexample for infinite graphs. But if I have a finite number of vertices, then we can prove this just by counting the valence of each vertex. And the way that we do this is for finite graphs, you use induction. And so, Okay, and then I have to remember, because I did this like at the beginning of the summer when I was writing up this worksheet. I was like, how do you do this one again? And I like convinced myself that you could use induction and that induction was great. And now I have to remember exactly what we need to conduct on.
I think you could induct on the maximum valence. Like, so if you have a graph that has as its maximum valence of any vertex is k, I think you can then move to k+1.
Induct on the maximum valence.
I haven't done this problem for the record, so if that doesn't like jump out to you as being correct, like you don't have to waste your time on it.
Yeah, I remember that. I think if I recall, the way that I did this prior was that you induct on the number of edges. And then for your inductive step, you just add an edge, right? And that increases exactly 2 vertices, the valence of each of those vertices by 1 each, right? And so, right, adding 1 edge to both graphs keeps the graphs homeomorphic, and it also keeps the number of, right, degrees of the edges. So yeah, which is why it takes so long, because like everything in this problem only talks about the vertices, right? So the base case is just no edges. And the numbers. Right? Because the only way that I can have 2 connected graphs with no edges is if graph 1 is a point and graph 2 is also a point, right? Or you could have 1 edge be your base case if no edges makes you feel woozy, right? Because, or this seems to be a contradiction to my statement, though, because the number of valence 3 and greater vertices here is the same for both graphs, but these 2 graphs aren't homeomorphic. So I guess we have to exclude loops. So there's a typo. Exclude loops.
In Schultz class, didn't we define those looped ones not to be graphs? Am I tripping on
Yeah.
that?
Yeah.
Never mind. I totally wrote this question perfectly because Schultz excluded this case. So instead of typo, recall that these aren't graphs in this Algebraic topology. That's perfect. I'm a genius. I totally meant to not. Okay, cool. So then for the inductive step, you assume that any 2 graphs with, let's say, n-1 edges such that the number of, I'm just going to call them good vertices for each graph are the same. Yeah, you let G1 and G2 be graphs with n edges. Okay, and this statement takes, right? So actually, I can't assume that they have n edges, right? I just have to assume that a graph such that the number of good vertices are the same. At this point, it's not clear that they have to have the same number of edges. Is this a problem with my induction argument? Or can you use like, right? So like this statement only tells me that I have the same number of vertices that have 3 or more, right? And that all those numbers match. So they have the same number of valence 3 vertices and the same number of valence 4 vertices, the same number of valence 5 vertices, right? So then the question is, right, we can rewrite, or we can replace G1 and G2 so that there are no vertices of valence 2, right? Because if this is in my graph, and then like these are blobs that do some other stuff, I can just replace that edge with a single edge, or those 2 edges with a single edge, right? And I get a graph which is homeomorphic to the original graph, right? So valence 2 vertices, I'm always allowed to remove, right? And so now I'm just looking at the valence 3 and bigger vertices and the valence 1 vertices. So now, how am I supposed to get around the valence 1 vertice problem? Because the thing that I'm worried about now is, oh boy, can I, aha, yes, versus all the, I guess that, right, following the rule that I just made, actually, no. I can fix this even so that way I don't have to. Wonderful. So here are 2 graphs which seem to have the same number of valence 3 vertices, but are not homeomorphic.
Yeah, I think I
Uh,
constructed one that has another similar pairing. Like do the Mercedes logo versus you have a central vertex, 3 lines coming off of it, and then attached to the endpoints a triangle. I don't see how
like
those.
this.
Yeah, so that's one. And then another one being you take the center of the Mercedes logo, but then instead of connecting the edges so that it's a circle, at each corner you put a triangle. So now there are 4 valence 3 vertices in each of them, but they
Yeah,
don't look like they could ever be homeomorphic.
yeah. So this could be that Jonathan lied to me because I stole this from his exercises to know worksheet. But I worked through it and I thought that this was fine.
If you weaken the statement from homeomorphic to homotopic, I think you might at least that's a step in the right direction.
These are
even-
still not homotopic.
Yeah,
This only
so-
has 1 generator and this has 3.
right. Yeah, so I was thinking,
Yeah.
yeah, so even that isn't enough.
Yeah. Okay, I think that 4 is actually false. Like we have 2 strong counterexamples, I feel like. So maybe there's a typo in this problem that was never corrected, right? Like maybe you need like some other condition on here to be able to deduce this. Or maybe there's a flaw in the original proof that he was thinking of. Okay, so I will email Jonathan about this, be like, hey, Jonathan, how come this isn't a counterexample to your problem? And then he'll be like, Jacob, you're being an idiot, because that's what normally happens. Okay, so I am sorry, Ryan, that I was unable to give a proof for question 4.
It's all good.
Okay, so I heard,
Could it possibly be that just the lower bound on K is too large? Like if you drop it down further, does it work?
I feel like we could do something silly with this example that I drew here and just like draw more edges and then like more things like this. And then just like add another 2 here and then just like add another, right? Just every time I add an edge between the 2 opposite ones, I just add, you know, the right number of edges to the corners on the other side.
Okay.
Oh man, 4 is frustrating because that feels like it should be true, but yeah, I guess that where the inductive step fails is that because before what I was thinking was that you remove an edge, you're left with 2 graphs that have the same number. So by the inductive hypothesis, they're homeomorphic, and then adding that edge back keeps the homeomorphism. Where that fails is that removing an edge might not keep the 2 graphs connected. Okay? And that's part of the assumption of the inductive hypothesis, right? And have to somehow show that, you know, no matter which edge you choose, the graphs are still connected. And that's, I think, not, and I
It's
think
not
that's probably
True.
where it is.
But like, look
Yeah,
at mine
so
on the bottom right.
Right, or the yeah, or the edge that I just pointed to. Because when you remove an edge, you have to keep the vertex there, because otherwise other parts might be. Yeah, yours also. Sorry, I didn't point at yours. My Zoom window was open, but yeah. So my
No,
guess is that
I didn't realize that you were pointing at one that worked because I forgot that the endpoints are distinct from the edges.
Yes. Yeah. So, okay. So I heard someone, Shanna, say like 10 through 14.
Well, and 9 because of the universality. Yeah.
Okay, 9 through 14. Any other recommendations, or someone that's just like out of those 5, do this one first?
Oh, I lied. Sorry, it's 10. You're right.
Okay, 10 through 14. Okay.
I like the
So it's-
diagram, so like 11 or something. But... And the homology, like 11, 14. Whatever people want to do.
In particular, you said 10 through 14. It took me a little bit of thinking, well, like once I figured out what I was like, how to like do things based on the identification space, I'm pretty sure I got 12. But if we could go over 12, that'd be great, because I wasn't totally sure that I did things on the identification space correctly.
Okay. So number 12, there are 2 ways that you could do number 12. There's like the hard illuminating way, and then there's like the easy way, which tells you exactly how this problem works, but doesn't tell you how to do any other problems. So we'll do the easy way first, that way we know what the right answer is supposed to be. And then the other way is to use the Seyff-Van-Kampen theorem. Okay. So the easy way is to note that this is the same as identifying right. So I have 2 tori, and instead of identifying the curves that I showed, I'm going to identify this top curve of this donut and the bottom curve of this donut. Okay. And then I get from donut that way. Stacked donuts. Which, if you look at it, looks like a stacked figure 8 cross a circle. Right? If you think about, 2 tori which are stacked on top of each other, right? I'm just taking a wedge of 2 circles and I'm just rotating it around the z-axis, right? Like the way that I drew it. So then the fundamental group of X, that's the fundamental group of the figure 8 space cross S1. And that's just the free group on 2 generators, direct sum Z. And if you look at like exercises to know problem 1, that's right. To know. Part B, question 1 is to prove this fact, that the fundamental group of a product is equal to the direct sum of the fundamental groups. So that's the easy way to do this, right? This is just be like, hey, if you choose non-stupid loops instead of the stupid loops that I gave you, right, you can just see what this is a product of, and then it's just the product of 2 known spaces that have known fundamental groups. Right? The other way right, is to use the Seyff-Van-Kampen theorem. And this is a good exercise of the Seyff-Van-Kampen theorem, because a lot of exercises that involve the Seyff-Van-Kampen theorem are like the wedge of 2 circles, but then like you try to like compute like what this like group is, and you're like, oh, it's the trivial group mod some relations, which is still the trivial group. Or it's like you're computing the fundamental group of a torus using the Cipher-Van Kampen theorem, and then what you're modding out is no relations, right? So this is like a really good exercise to go through because the thing that you're modding out has a relation, right? So like this is really good because it like really gives you like some meat and potatoes on like how the Cipher-Van Kampen theorem works, right? And there's two versions of the Cipher-Van Kampen theorem in Moncrief's. There's like the first version, which is like a purely categorical version of the Cipher-Van Kampen theorem, which you should feel free to safely ignore. And then like later, like the very end of that chapter, there's a classical version of the Cipher-Van Kampen theorem, right? And that's the one that you, in my opinion, want to learn because that's the one that lets you like compute fundamental groups, right? Like the other one is just like cool, it's like shows you that it exists and it like shows like all these nice like super theoretical properties, but like for the qual, when you're using the Cipher-Van Kampen theorem, it's because you want to like compute the fundamental group of something using the Cipher-Van Kampen theorem. When you want to do that, you want to use the second version. So what does the second version of the Cipher-Van Kampen theorem say? Maybe I can try to remember this. Is that the fundamental group of a space X is equal to the free product of the fundamental group of U and the fundamental group of V mod the least normal subgroup generated by loops in U intersect V, right? Where, I should say, where U comma V are non-empty and U union V is equal to all of X. Right? And I think that you might also need the assumption that like X is connected or something like this. So I'll add this in parentheses because I think you need that X is connected, but I'm not sure. It certainly seems like you would want X is connected. Otherwise, you just like, although maybe this is a way to prove that like the fundamental group of, yeah, right. Because otherwise the fundamental group of a disjoint union doesn't make any sense, right? It's just like, it depends on where you put the base point and we don't want to, yeah, so X has to be connected. So the way that this hard way works, so I'm going to draw two sets of my space. So U is going to be the entire left space and an open neighborhood of my red loop. And V is going to be the entire right donut and an open neighborhood of my loop on this side, right? So the intersection, if I'm going to try to draw a really poor U intersect V here, right? That's going to look like, okay. It's going to be like a, so you have like one torus from here and one torus from here. Hopefully this makes sense. So like it, like, so from like a top down kind of drawing, this is hard, but like you imagine like a center ring and there's like a an outside cylinder and an inside cylinder, right? So you could draw this as like a little cone bit here and a little cone bit here. So we could do something like this, I suppose. right? So like this is, here we go. Make this solid. Right, so you have like two tubes inside of each other, and you shrink the outside tube and you expand the inside tube if you draw it like this, right? So like one way that you could draw like these two tori with like the original identification is you could draw a torus inside of a bigger torus, right? And then like pinch the outside torus at that curve until it just barely touches the inside torus. That would be another way to draw this. Or you could just stack the donuts on top of each other, right? This is like stacking the donuts on top of each other, but inside of the torus. So if you do it the way that the original identification goes. Anyway, so the rest of the Seyff-Van-Kampen theorem, if you like call these loops names, the computation isn't too bad. So here's alpha, and we'll call the other one here, let's say gamma. And then on this side, we had beta, and we'll call this one delta. Okay. And so the Seyff-Van-Kampen theorem tells you that the fundamental group of X is equal to the free product of the group generated by alpha and gamma, such that alpha and gamma commute. Right, free product with, we have beta and delta, such that they commute. I'm just gonna write commute. Mod by, okay. And I just kind of wrote this, so recall that like, if you're given S a subset of a group G, right, this is the smallest subgroup containing S. But if you put a bar over it, at least this is pretty common in the Seyff-Van-Kampen theorem, right? This is the smallest normal subgroup, which contains S. Right? And you need it to be normal because otherwise you can't like mod out by that subgroup, right? You can only mod out by normal subgroups. So most of the time you just need to know which loops are in the intersection, right? But you know, for official technical reasons, you need to mod up by the least normal subgroup. And so in very rare cases, you get more loops than you were expecting, but most of the time you just get the loops that are in the intersection. Right. So let's see. So then I want to mod out by the smallest normal subgroup containing these things. So this is going to be the smallest subgroup, which contains alpha, which I will note here is equal to beta. And whenever you mod out by a group, if you find generators for the group, those generators, the generators that you mod out by become the relations in the group that you modded out by, right, as a general rule. Right? So this becomes, as a set, words that look like alpha raised to some power, gamma raised to some power, followed by beta raised to some power, followed by delta raised to some power, followed by alpha raised to some power, followed by gamma raised to some power, on and on and on, with the new relation that alpha and beta are now the same. And I don't want to like specify what the powers are, but like it's a free product, right? And I don't know how familiar you are with free products, right? But free products generalize free groups, right? So if you have, right, so like the free product of group H with group G, this looks like the set of all words, which is an element of G, right? followed by an element of H, followed by an element of G, followed by an element of H, followed by an element of G, dot to dot, followed by an element of H, right? Where like the end elements are the identity and and the multiplication is just concatenation followed by whatever group operations you have between two elements that come from the same group, right? So like G, H, G1 times G2, H2, G3, right? Like you're just like, hey, these are from the same group, so we just push them together into one group element, right? That's how the free product works. And essentially what you get is that, hey, since alpha is equal to beta, right? And I also have the relation that like alpha and gamma commute, and beta and delta commute. I'm being very sloppy with the solution, but that's what happens when you get to algebraic topology, right? Alpha and beta are the same. That's the relation that I get from this modding out relationship. So I could write out, right? It's the same words, right? But now it's just that delta and gamma do not commute, but alpha commutes with everything, right? So alpha commutes with everything. Right? And so that means that I can take any of these original words and push all of the alphas to the right. Right? So I can move all alphas to the right, and I get all words of the form gamma to some power, delta to some power, gamma to some other power, delta to some power, and this goes on and on and on. I know those look like M's, but they're supposed to be squiggles. And you get like gamma to some power, and then delta to some power. And then you get a bunch of alphas at the end. And it turns out that, hey, all of these words are exactly identified with the free group on two generators, and this is just a cyclic group. Okay. And so you get that this is the direct sum of F2 and the integers. And perhaps this isn't the best explanation of this problem, but we knew what the solution was supposed to be, right? And so going through the details of this problem is worth it, especially now that you know like what you're supposed to be looking for. But like this is kind of how it's supposed to shape down.
Yeah, so I ended up biffing this one because I couldn't read my handwriting apparently, or I didn't remember why I noted something with a star. And so I only got the free group on two generators, I think. But could you do this using the identification space for the torus itself? Because that's how I tried doing it, where you flatten out the tori into squares and then identify edges.
Oh, okay.
I'm sorry for like just monopolizing Shauna's questions, but
I
right.
hope we get to
Okay.
the other ones. Yeah. Okay. Thanks.
Yeah. So yeah, it should be possible to do this using the identification space where you just like make these alphas and you make these also alphas, and then you make this like gamma and you make this gamma, you make this delta and you make this delta, right? And then you just like try to glue these together. And this actually looks like it might be easier than using the Seifert-Van Kampen theorem. Because,
oh no, I ended up using the Seifert-Van Kampen theorem, but then I biffed it because I noted something with a star and then forgot what it stood for, I think. So then I ended up getting the free abelian group on two generators somehow.
yeah, that's interesting if you glue these two alphas together, right? And then you get like,
Yeah, no, what I was saying is you
Yeah.
don't
Okay,
glue
anyway.
the two alphas like that, but you don't get rid of the line in the center. And you draw your loop, your regions using that, but I guess I must have messed up.
Yeah.
Badly.
Yeah, I think you can do it this way. It's just not how I approached it, but yeah. Okay, cool. So that was 12, or at least I'm gonna say that that was 12. I'm gonna put a box here as if I had done something. Okay.
I think we can try 11, like 11 or 14.
Yeah, let's try 11. And we kind of talked about 13 last week. I
14.
put that on. Yeah, I talked about 13 in the worksheet
14?
on Thursday.
Oh, okay, that's right. Yeah, 13. Mhm.
So okay. So yeah, let's try 11. And if we don't get to 14 till Thursday, that's fine,
Sure.
because Thursday I'm planning on focusing on homology and 14 is about homology. So let's okay, so 11. Okay. So we're going to let X and Y be connected semi-locally simply connected topological spaces, and let these be universal coverings with these covering maps. Okay. And then we get this commutative property. These maps are unique. And then, okay, neat. Okay, so for the first bullet point, let's talk about the first bullet point. So
Just in general, are we always guaranteed a universal covering, or do you need, the specifications of semi-local, simply connected, quasi-compact, whatever? Do you need 12,000?
Wikipedia claims semi-local is very important for that.
Right. How do you-
semi-locally simply connected is exactly the condition that says there exists a universal cover,
That's what I thought. Okay.
right? In fact, those two conditions are, there exists a universal cover if and only if it's semi-locally simply connected.
Right.
So we have a diagram, right? Diagrams are great. F, Px, Py, okay? And I want to find a function on the top. The way to look at this is actually to just draw this diagram slightly differently, so that way it looks more like the lifting criteria, right? So if I draw this like this, right? So now I have a continuous map along the bottom, right? And so maybe I should write out what the lifting criterion is, right? Or the lifting property, right? I suppose that since we're talking about classical covering spaces, this is a property, not a criteria. I'm used to thinking of it as a criteria. So recall, if you have the following diagram, I'll call this like G from Y to, we won't use Y because we've already used Y. The problem, we'll say Z, we have a base, we have a cover, and this is a cover, right? Such that the induced, right, the image of the fundamental group is a subgroup of the image of this fundamental group. And in fact, I should probably write this as a pointed space. So let's go E, B, and let's go little z. So that way I can just specify what the base points are. And if you haven't seen these pointed maps before, all that this means is that there's a function g which sends z to b, such that g of little z is equal to little b. Right, that's all that the pointed space notation means. It means that, right, my sets, I have a continuous map, and I'm telling you that this point goes to this point. Right? And pointed maps are important for studying like fundamental groups and covering maps because, right, fundamental groups are pointed, right? And the way that the fundamental group interacts with the covering map depends on this base point correspondence deal, right? So keeping track of this, right? If I have this diagram such that I have this interaction between the fundamental groups, then there exists, and I'm just going to draw a blue thing, and I'm just going to write a lift G tilde. I should just write G tilde. Which sends Z, Z2, EE. And in fact, I can even say that there exists like a unique G tilde which does this. right? Because I'm working in pointed spaces, right? The uniqueness is up to choice of E in the preimage of the base point V, right? So if I change the preimage of my base point, right, then I get a different lift of the map, right? So what you often hear is that like, so paths always lift because the fundamental group of a path is always trivial. So it always satisfies this condition for every cover, which is why paths lift. And that's like the thing that you care about for covers, right? You want paths to lift uniquely up to choice of base point, right? And this pointed map, this Z to E, right? You just use 0 as your base point here for your path, and then you get a unique lift up to the choice of base point that you care about, right? So here, the way that we do this first bullet point of 11 up here is we say, hey, this X tilde is simply connected because it's a universal cover, right? So this means that the fundamental group of X tilde, this is trivial. And so that means that the image under, which one do I do first? It's not PX. F composed with PX, the induced map of this is still trivial, right? Because the image of the trivial group is trivial. So it's contained in this image, which is also trivial, right? But that means that there exists a lift of this map. Okay. And then you straighten out, right? You turn the triangle back into a square, and this dotted line that I just drew is exactly the dotted line here, right? So if you call this map F tilde, even though it has like this PX in front, right, you get a map between the two covers. So this is just a use of the lifting property. And then the second bullet point is no different F tildes for each choice of base point, as I just explained, right? Different base points give you different lifts.
So this problem is literally just remembering that the lifting property exists.
Half of the problems in part B of this list of problems is just, do you remember that the lifting property exists? Right, like, so for example, you mentioned one problem on the Mock Qual. Question 4 of the Mock Qual, this question. This is just lift the map to the universal cover. The universal cover is contractible. Then push that contraction down through the covering map to get a contraction in the face. That's the proof. Right? And if you just follow that through question 4, that's how question 4 works.
Did we get the third bullet point, Jacob?
Yeah. So the third bullet point is in here. This is a theorem in Moncrief's. Okay. And if I remember, one of these directions is straightforward, and the other one requires some thought. But okay, so and since we only have 5 minutes, I will try to give ideas rather than try to write out details, right? But so here's the idea, right? So if I look at elements in, okay, so the first idea is that since this is a group homomorphism, right? F star is a group homomorphism, you just have to show that the kernel contains only the constant path, right? Because that's how you show that group homomorphisms are injective. You show that they have trivial kernel, right? So to do the forward direction, you assume, right, that like alpha has f star of alpha is equal to the constant map or the constant path at the base point. And then you want to show that actually alpha is just the same as the constant map at the base point. Right. And the idea behind the universal cover is that the universal cover unloops all loops. Right. What do I mean by that? Is that like if I have my base space down here and I have like the constant loop and I draw, if every color is a different homotopy class of loops, right? Then in the universal cover, what this does is this exactly identifies, once you choose a base point, different lifts of paths.
I'm sorry, can you say that part one more time? You said the different colors are the homotopy classes of the groups, and you said what?
Yeah, so yeah, different homotopy classes of paths. So i.e. different
Paths.
group elements of the fundamental group.
Right,
Right.
and then what's in the
Yeah.
top? Yeah.
Yeah,
okay.
what the universal cover does, so this is the universal cover, right? The good cover, right? The way that you construct covers, right? The heuristic is that covers unfurl loops, right? They undo loops, right? So like if you take like the torus is the easiest case to example. You choose one of those generating loops and you undo it, you get an infinite cylinder, right? So you take that loop and you undo that loop into a line and you get an infinite cylinder, right? Then you take the other loop and you unfurl that loop and the cylinder unrolls into a plane, right? And that's kind of the mental picture that you should have for like all loops and all covering spaces, is that the universal cover unloops loops. That's a fun thing to say 3 times fast. Right, so if alpha is constant, then alpha is represented by this black thing, right? Oh, this is, so then I have a y and I have y tilde up here. Okay. And so this is saying that, hey, so I guess that alpha is, yeah, alpha's on the right. It's like one of these loop things. But I know that whatever alpha is, it goes down to a single point. And like this should be a problem. Or it shouldn't be a problem.
I'm sorry, which one's alpha?
Yeah, so alpha is one of these loops on the bottom left.
Bottom left, okay.
Right. Yeah, sorry, I'm not being super clear, but that's because I'm both trying to go fast and I'm trying to go fast. I guess I should just say that I'm trying to go fast. Okay, so right. So given a loop in the base, I can always pick up a point in the cover via the lifting correspondence. That's the goal here, right? That's the thing that makes sense here, right? Right, and this is by the base point projection, right? So the way that this correspondence works is that you take a loop gamma in the base, and normally I don't parameterize my loops, but let's say that, right, this is my loop, it's parameterized between 0 and 1, right? Then you lift the loop to a path in x tilde called gamma tilde, right? So, and that's exactly what I drew here, right? These loops in the base lift to paths up in the universal cover, right? And the lifting correspondence, right? It sends the equivalence class of gamma to the endpoint of the lift. Right. And this gives you a correspondence. This is actually for a universal cover, right? For a universal cover. This is a bijection between the fundamental group of the base and the fiber over your chosen base point. So every loop gives you a unique point up in this fiber. For this direction, we're assuming that F tilde is injective. And so this gives me exactly, right, another set of discrete points, right? And by the construction, this is also the fiber over this base point. So this is the pre-image under Y of F of X naught, and then you map that down and you use the way that we constructed F tilde to say that this is exactly the, right? Then you can go backwards basically through this construction, right? Right. In order for alpha to be constant map, right, you take the preimage of the constant map here, it's injective, so it has an exact preimage over here, and then you map that down, and because of the lifting correspondence, this has to show that alpha is trivial. I can't state more details, but I'm now convinced that using the lifting correspondence is the way to go here. And this is a theorem proved in Mock Qual, so if you search through Mock Qual, you can get a much better proof, I'm sure. So
Yeah, I forgot. When are office hours? Thursday or something like that?
I haven't announced them, and that was one of the things I was going to talk about today, was
Oh,
that I'm
okay.
going to have office hours. They will probably be, Wednesday is when I have the best availability.
Okay.
But I'm going to use the original win to me to try to choose some times that a lot of people can
Mhm.
attend, right? So
Okay, yeah, because I know we're out of time, but I have more questions on this one. So
yeah,
just to see it nicely written, because I couldn't do that, you know.
yeah,
But
this is a problem that I remember doing several times while I was studying for the quals. So it's been 2 years, so the details are rusty, but I know
Good.
that the solution exists and it deals with the lifting correspondence. As soon as I realized that, I was like, yes, that's the key, is the lifting correspondence.
I
So,
like it.
okay, I'm over time by 3 minutes yet again. Something tells me that this is going to be a theme, right? So we should just celebrate it as a theme instead of, but I do have to go at 10. So if there are any questions, feel free to send me an email. I'll send out an email with office hours, probably by noon.
Great, thank you.
And if there's any suggestions for homology problems for Thursday, Thursday we'll probably do homology type stuff. So feel free to send those in.
Thank you.
Thank you.
Thank you.
Yeah.
Thank you so much for you. Bye.
Thanks.
Thank you.